So our next speaker did his PhD dissertation in space-time singularities in superstring theory. We're all clear on that? He is a scientist who is working on an amazing project at the moment, a global research project aiming to design a spaceship that will be launched towards a nearby star in our lifetime. He currently lives in Anchorage, Alaska, where he holds the position of Chief Scientist for Variance Dynamical Corporation. His PhD, as I just explained to you, it's much longer than that, and I don't even understand that part. But he's going to talk to us today about reaching for the stars and how we can accomplish this kind of amazing thing in our lifetime. So will you please welcome Dr. Andreas Tziolas.
Good morning, everyone. It's such a wonderful opportunity to be here, traveling from Anchorage, even for this brief period. It was a lifelong ambition to come to Australia. And it's been a lifelong ambition to motivate a journey even further from that, and that's the subject of my discussion with you today. The organization that I present is called Icarus Interstellar, and our purpose is to generate interest in a type of study that's been ignored and that's only existed in flights of fancy up till very recently. But we need to start somewhere else. We need to start by just asking a couple of questions. What do we see in this image? Is it an opportunity to explore a hole? Are we thirsty? Do we need to pull up some water and drink? Are we architects and we're exploring the way that this well was constructed? Maybe we're archaeologists and we're trying to figure out how long ago this well was built. You know, does this image conjure up fear? Because I have to lower myself down to go and explore something. Maybe I drop my keys in there or something. So when we're presented with an issue, we conjure up feelings that are very, very personal and subjective. There's no catch-all for any situation. How far would you go? Someone shows you this image, or you're standing on a dock, and you're considering how far away can I go here? But am I in a boat, or am I swimming? Do I have a dock behind me? Am I exploring on the surface of the water, or am I exploring underneath the water? Am I going to have enough time to explore and to complete my objective? Because the sun is going down. Where's the sun coming up? And I have the entire day. Again, everything is subjective. So, if someone told you, if you looked at this image and someone asked you what did you think of, and you said, I really want to go there, we still don't understand what the question is. We still don't understand what the answer was. Do I want to go and explore this desert? Am I a Bedouin, for instance? Or is the question asked for me, for instance, so that you would assume that I would want to explore space? Again, it's not clear what exactly the answers are. But it's clear that we have motivations and that we have aspirations. So someone wanted to explore space once upon a time. And these are the orchestrators of the space age. It didn't just happen. It was orchestrated very carefully and skillfully. These three gentlemen, Dr. Van Allen, Dr. Chapman, and Dr. Berkner, were physicists who around the 1950s decided that they needed to explore the ionosphere. Ionospheric physics was all the rage. But in order to do that, they needed to be able to travel and do around the globe experiments. They needed to go to every different place, but there was civil unrest. You know, there were political climates that didn't allow that kind of motion, especially when high technology, experiments were going to be conducted above my atmosphere, right? There's some certain apprehensions. So what they did is they decided that they're going to. This meeting happened in 1950, and they decided in 7 to 8 years, they're going to design a geophysical year. during which they're going to challenge the entire planet to explore space. And they made sure that they positioned themselves as chief scientists for the Explorer missions, president for the Special Committee for International Geophysical Year, surprisingly, and the president of the International Council of Scientific Unions, who would have to approve this. So they said, this is what we want to do, let's position ourselves as pawns in order to approve what we want to do, and let's get our science done. Van Allen discovered the Van Allen belt. It protects us from harmful radiation from space. That's why most of the space occupation in space happens in low Earth orbit, because the Van Allen belts protect most of the radiation. Dr. Chapman confirmed his theories and confirmed that the ionosphere works in the way that it does work, and that gives rise to long-term radio communications. And then follows an age of wonders. This wasn't their objective. This is what happened as a consequence. NASA is formed. The Saturn V rocket is constructed. It leads to an amazing race with all of the motivations that come behind it to land a person on the moon. But it's done. And all of this is done within 10 years of the time where these people dreamed up this geophysical year. The construction of cookie-cutter almost spacecraft ensued. So the Mariner missions explored the terrestrial planets. There was no stopping them. The Voyager and the Pioneer missions explored the gas giants. We had human occupation in space, in the Space Lab and in the Mir space station, which was a remarkable object, and at the time to have in orbit and to have such prolonged human occupation in space. And all this happened within just a couple of decades of people having a dream of exploring space. So what did we learn from all of this? Was there some, wonderful discoveries? We discovered some interesting things. These were all curiosities at the time. We discovered that there was water on the moon. We discovered that Venus was really hot, and it had sulfuric acid rains. It's probably not the best place to imagine, to go and explore. We explored Mars, and we have all of these little rovers crawling around Mars looking for life. They're looking for life. I know that NASA says that what we're looking for is signs of geophysical activity. What they're looking for is life. We've figured out that Europa has oceans. Europa is one of Jupiter's moons. Underneath Europa, about 2 kilometers down, there's a liquid ocean that surrounds almost the entire planet. There's enough heat from inside the planet, the moon, to heat that up to the point where it's liquid. So you have heat, you have water, you have all of the conditions that gave rise to life on the Earth. So that would be an interesting place to explore. We looked at Jupiter and we figured out that it's really stormy. And then we continued exploring. We went to Saturn, and one of Saturn's moons, Titan, had something really surprising. It has an atmosphere, but even better, it has storms. So now there's an energy source in a mostly methane-rich atmosphere, and that energy source, through the discharges, gives rise to amino acids, the same way as it did on Earth. There were some frowns down kind of situations. There was all of a sudden Pluto was devalued as a planet. Pluto is just a dwarf planet. It's not one of the others. But it found a family of its own, because we also discovered Ceres, which some of us maybe don't know about. And Ceres is another dwarf planet that is in between Mars and Jupiter. And it's a perfectly sized planetoid, or dwarf planet, for human exploration. Because the gravity is so low that we could send a spacecraft there, we could land, and then you don't need that much fuel to take off. Plus, it's mostly ice. That sounds really interesting. But we found some other remarkable things. We found that there's a black hole at the center of our galaxy. That's remarkable. The Milky Way has a black hole. We theorized it, but we didn't really know that it was there. Look at SO16 on the left side. This is images of the center of our galaxy, and we just took pictures, and we saw that remarkable object just swinging around a point at an enormous speed. But when we look at that point where the star is, there's nothing there. We calculate its mass and we find that it's 4 million times the mass of the sun. Say you don't believe in black holes. So there's nothing there, we can't see it, not that there's nothing there, but it has a mass of 4 million times the mass of a sun. That's a pretty good description of a black hole. So we've discovered black holes. So what? So what? So I'm interested in this, right? I'm interested in this. You're not interested in this, right? But we benefit from it, okay? We benefit from this. We have global positioning satellite network. We have all of these technologies. I won't go through them, just want to flash them in front of me. I have all these technologies that were born out of this technological surge, this scientific focus that occurred during the dawn of the space age. And we're still benefiting from it. But we benefited from it in remarkable ways. Like we started living in a post-futurist, post-modern era. Artists started conceiving of living in the future. They started designing. They started conceiving of humanity working and interacting in spaces that weren't square boxes anymore. This is a part of an artistic exploration that defines what it is to be human. To the point where, someone designs this, this resort that looks like a saucer section from the Enterprise. Just a remarkable feat of engineering. And why would you ever build it like that? Because you have an aspiration, you have an aesthetic a desire for it to look like this. All right, that's great. Now we're cooking with gas, as they say. So what's next? What's next for exploring the space? Well, we have the successors of the space shuttle called the Venture Star. There's the spacecraft on the left. We have the successor to the Hubble Space Telescope, which is called the James Webb Telescope. It's 30 times more analysis capability. We have successors to the Saturn V rocket, the Orion and the Constellation programs, which are designed to take people to Mars. And we have really cool ideas for capturing asteroids and exploiting them because they're a remarkable resource. These are all things that were canceled. What happened? NASA employs 18,000 scientists, has 18 research centers. And we complain that NASA's budget is continuously dwindling. The uncertain climate, NASA's uncertain budget. That's NASA's budget. Does that look like it's dwindling? That's just data. I'm not manipulating anything here. That looks like a constant budget. I would love to have $18 billion to explore space. So I started investigating what's going on, because there's a lack of motivation. What's going on? And I looked at sort of the centers of exploration, which are the companies. So but around 1985, there were 26 companies that were born, that were fused, that were products of the space age. Those all started getting fused consolidated into only 4 companies. That's in the United States, and this is in Europe. The same thing happened. Remarkable that there's also 4 companies being consolidated. I looked at employability, and physicists and aerospace engineers don't actually go into aerospace companies anymore. They go into IT, or they try to dream up an app that's going to make $1 million overnight. So who's going to do the work? Where is this innovation going to come from? It's not going to come from me or from these 60-year-old other guys that don't know how to log into their iPad. It's going to come from the fresh new brains. And then people start looking at the investment. Is it worth investing? Like big companies, is it worth investing in space? And they see that the percent return on investment is dropping. So, it was good, but now it's kind of going away. However, they failed to see that the nominal return on investment for space research has actually doubled. What does this mean? I ventured into this financial analysis things and hated myself for it because I didn't really understand it. But during the Apollo era, for every dollar that you invested in space research, you got back $7, okay, through moving industrial machines, from education, from salaries, from taxes, from returns. Today, that's 14 to 1. So this job is not a return of investment, it's industrialization. We build things faster, we advance faster. So what happened? What happened? I believe that the lack of transformative innovations since Apollo is to blame, that the propulsion systems are virtually identical from what they are now to what they were then. The Saturn V was capable of delivering 120 tons to low Earth orbit. The best possible conceived of spacecraft, space delivery system can deliver 53 tons. And that's the Falcon Heavy, SpaceX, Elon Musk, SpaceX. Another problem is the spacecraft, the rocket on the right doesn't actually exist. It's conceived of. The Saturn could deliver 45 tons to lunar transfer orbit. It could take things to the moon. The Saturn V, the Falcon Heavy can't go to the moon. It can go as far as geotransfer orbit, geostationary transfer orbit, which is where we drop off our satellites. 50-year-old technology is only now being space-proven. Why? Why? Why aren't people pushing? Because those young people aren't being employed in those big companies anymore. That's why. Solar sails, ion engines, plasma thrusters. The Japanese, a couple of years ago, only just space-proved a solar sail with remarkable success. They showed that it worked. There's engines, remarkable engines like the Vasimir engine, which is this crazy magnetohydrodynamic thruster with incredible capabilities, but it hasn't been space-proven. There's progress in advanced spaceflight has been lost. We've failed to foster the successor to the Saturn V. The machinery, all of the companies that went into producing the Saturn V don't exist anymore. And this is because we don't understand how look at this suit that this person is wearing. You're telling me over the last 25 years they couldn't, kind of upgrade that suit a little bit? It looks identical. There's no advance. And what is this person doing playing chess on the International Space Station? He should be tending some crops. He should be trying to live in space, not camp out in space. We camp on the International Space Station. We don't live. There's no terrarium. There's no grow some kale or something, Grow a strawberry on the International Space Station. Why not? Because we need to live in space, not just occupy it. Progress in nuclear power and propulsion has been ignored. Human colonization of the moon and Mars got pushed back by 50 years. We had the highest energy concentration that we can achieve as human beings right now lies in nuclear power. And we designed a nuclear thermal rocket, but it was canceled. Why? Because we feared nuclear power somewhat, especially in the United States, regardless of the fact that these blocks to the right represent how many deaths per watt produced correspond to coal, oil, and nuclear power. Nuclear power is safe. It's just perceived as unsafe. The biggest problem is that there is no clear target or objective for space exploration over the next decade. We don't know whether we're going back to the moon. We don't know if we're going to explore asteroids. We don't know if we're going to go back to Mars. Every political leader uses this as a platform and changes the direction. The problem is someone is paying the price, and that's that little fellow there. What motivation do they want? Do they have to be rocket kids? To do what? What exactly are we trying to do? I think it's time to take matters into our own hands. And let's go to a star that's not too far. And we're using this imagery as a target, okay? And we're setting a course that's so far into the future because it's really, really hard to do. Let's set a goal that's so difficult that any progress we make towards that goal has remarkable consequences for the technological backbone that drives human exploration of our existence on the planet. We're defined by the technology that we use. So let's strive for something, for a goal that is solid and cannot be changed. If we try to explore interstellar space, then we can explore everything else. And people are thinking the same thing. It's not just me and my little organization. Kepler and NASA and the co-wrote, there's a couple of missions that are exploring space, and they're looking for planets. They're looking for planets around other stars. Even the Europeans, which are usually very frugal with their spending, are designing very large telescopes, 4 to 5 meter telescopes, and they cite as one of their primary objectives the search for planets around other stars. And that's because this research is inspiring. We found 5.5% of all stars of all stars have planets, have Earth-sized planets. And we've also found that Alpha Centauri has a planet. And Alpha Centauri, the closest star to us, has a planet called Alpha Centauri b, little b. And it's around Alpha Centauri b. It's too close to the sun. It's probably too hot for humans to inhabit, but that doesn't mean that we didn't find a planet there. And if there's one, there's going to be a lot more. Alpha Centauri, which is the closest star, because we're trying to define a goal now, right? What exactly are we talking about? Alpha Centauri, there's actually a network of 3 stars there. So that's incredibly beneficial for us who are looking to explore something. Proxima Centauri and Alpha Beta Centauri are these 3 stars that are orbiting around each other, and they're right in their neighborhood, only 4.3 light years away. And if you're wondering where Alpha Centauri is, on the map of this near interstellar space, it's, if you're on the equator, you look, well, from where we are now, I guess you just look directly up. But usually when I'm in Alaska, I say you look down 60 degrees, that's where you are. From where we are now, we look directly up. That's kind of weird, but yeah. Alpha Centauri is directly above us. But once we find a planet, how are we going to go there? We realize that no one's really looking at this problem. And now they say that you lose a third of your audience every time you show equations. So I'm just going to cut to the chase, is that if you look at the problems and you say that you want to get there within 100 years, traveling at a fraction of the speed of light, then all things considered, you need to improve on what we can do right now by 15,000 times. So my spacecraft, my materials, my metals, my life support systems, everything has to be 15,000 times better than what I can do right now. So that ends my talk. I'm going to go home because it's not achievable. But someone pulls me back and says, hold on, we've done some pretty incredible things. 1903, we flew, and then 50 years later, we flew in space. And then 10 years later, we went to the moon, and a couple of years later, 20 years later, we are existing in space. So we tend to underestimate what we can accomplish in large time scales. Human achievement over 50 years quantified, like what is the horsepower of a train, which was the fastest means of communications. Between the 1950s and 1930s, it kind of reached a peak. It was around 5,000 horses. The Saturn V can produce 160 million horsepower. That's 37,000 times better. So that's easier than what I'm talking about, traveling to another star. A rocket the difference between a rocket and a train, we can do this. And that's because we set a goal. That's because we set a goal. This is what the world looked like, this quaint image, when J.J. Thomson discovered the electron. Okay, 1897, almost the 1900. People are like riding around in these unicycles, and there's a guy in the lab behind there discovering the electron. This is what the world looks like today, when we discovered the Higgs boson, when we conceive of dark matter, when we have understanding of how to measure quantum vacuum energy. Like, science is progressing at remarkable rates. How quaint is the difference between those two images? That's how peculiar it'll look over the next 100 years. We'll look back at that image and think, oh my gosh, what were they doing? What were they like? The British Interplanetary Society conceived of a similar question. How can we explore space? How can we explore interstellar space? And they designed a spacecraft called the Daedalus in 1978. This was the first spacecraft that proved that science and technology today could be used to explore space, to explore interstellar space, and to travel to another star. It was a very, very large spacecraft. You need a lot of fuel to travel to another star. You need fusion power. You need remarkable shielding technologies. You need to be able to keep this thing running for hundreds of years unattended, 50 years for the Daedalus. But they showed that you are capable of achieving fractions of the speed of light, 13% the speed of light. The spacecraft could theoretically achieve if we set this as a goal. But that was quite a long time ago. So just around when I was finishing my PhD, some of my friends approached me and said, we need to, Richard Obusi, Kelvin Long, and a couple of other folks said, let's do another Daedalus. It literally started like that. We'll call it Icarus, like the son of Daedalus. So what we did is, with a lot of trepidation and flies in the gut, and we approached the Daedalus, the old Daedalus team, the surviving Daedalus team, and they said, do you guys want to give us your blessing to sort of continue this work and do another interstellar spacecraft? And they said, of course. So we had a really heartwarming meeting at the British Interplanetary Society in 2009. The team on the left are some of the Daedalus team. The people on the right are the initial Project Icarus teams. And that's how Project Icarus was formed. So what is Project Icarus? We said that we want to see whether or not we can train a generation of interstellar engineers, because no one does this. There's not a degree in interstellar engineering. We wanted to see if we can use crowd research to drive space exploration, because we want everyone to feel that they can participate. I want to be a part of it. I don't want just NASA to do it, or just the European Space Agency to do it. Where am I in this equation? I want access to this. I have the capabilities. Or I don't have the capabilities, but someone needs to teach me. So we wanted to train a generation of interstellar engineers. But we need to set a solid research objective. We're not just using fusion, we're just not just using warp drives and we're going to make it look pretty and you're going to jump in and press a button and then you're there. Where is the science? Where is the physics? Where is the engineering right now? And what projections do we need to make in order to make this a reality? So we built a team of Icari. And the team swelled very quickly. We doubled in size almost every year. We currently have 66 designers for Project Icarus out of 8 countries, an average age of only 36. And we've published 55 papers, attended 25 conferences, done 140 internal trade studies in 3 years. So we outperform most university departments in terms of productivity. We have very, very solid research objectives. We have a private sector research and development model, so every time you have a down select of systems, it has to pass certain phase gates, so it's not wishy-washy. And our purpose is to derive a technological roadmap for the stars. So every time we reach a problem, we analyze the capabilities and the problems, and we say, we need to focus on fusion, we need ultralight materials, we need nanotechnology to go in this direction, we need this and that. That's a roadmap. A roadmap for interstellar travel does not currently exist. So we designed some interstellar precursor missions, a satellite, then a mission that would go to the moon, then a mission that would go out to 100 astronomical units, then a mission that would go out to 500 astronomical units just outside our solar system. And then the Icarus was born. So we have the Mark I Icarus, we started fleshing it out, the Mark II, with shielding, magnetic nozzles, things that don't traditionally go into spacecraft. We designed and fleshed out the engine. We figured out how it would work, if this is an internal confinement fusion engine, for those of you who are curious. But we started getting serious. This thing would get really hot, so we'd have to figure out how to cool it, thermal modeling, really advanced things like thermal load modeling, diffusion aperture scaling, things that haven't been really done for spacecraft. This is why interstellar engineering is not the same thing as aerospace engineering. This is a lot harder. Then we started generating some permutations, antimatter engines and things like that. So the Varies was born, different types of engines. And we looked at what we had done. We looked at what we had learned over a couple of years. This was about a year and a half afterwards we had generated this work. And we looked at it and we saw that we know quite a bit about spacecraft. And we know quite a bit about planetary systems also. So we did something fun. We took the Avatar solar system from the movie Avatar. And we wanted to see how well our models add up. And we put them all in a model. This is a good friend of mine, Martin Fogg, generated these. And he said, do they work? And he did stability analysis, and he said that it's not going to be, it doesn't work. It's not like that, not quite like that. But we learned how to build solar systems. which could be fed by exploration from the searches that the Kepler spacecraft was doing. And then we realized that we really need to get organized. We can't just do this as Project Icarus anymore. So Icarus Interstellar was formed, and we set ourselves a mission. Our mission was to realize interstellar flight, and initially our mission statement said before the year 2100, but I've had a change of heart. I don't think I can wait that long. We will accomplish this by researching and developing the science and technologies that will make interstellar flight a reality, igniting the public's interest and engaging with all those prepared to invest in interstellar exploration to make space accessible to all, and the future of mankind and the technologies that spin off of it need to benefit everyone. So we started doing some research. We started spinning off other projects. We had Project Hyperion, which is human-occupied interstellar vessels. Because Project Daedalus and Project Icarus are robotic probes, there's no humans on there. It's really hard to put parasites in the spacecraft. They really ruin your design. So we've come up with some you have to keep on feeding them, it's colonized interstellar vessel. We run some numbers. We figure out what a spacecraft that would have a crew would look like. What the interior would look like. Just some ideas. Okay, we've only been around for 3 years. It could be better. This is work ongoing. We looked at space nuclear power and propulsion, which was abandoned. So let's get some people working on it. Let's see where it could go. It could take us to Mars pretty fast. It could lead to interstellar precursor missions. We looked at solar sails and beamed interstellar vehicle studies. So this is a spacecraft that has this huge sail in front of it, and there's a beamer probably concentrating the light from the sun that makes a railway. And the spacecraft sits on that railway and pushes it along, kind of like a kite. And we did some analysis on the stability of the sail. This is some work that Jim Benford did. But we also did some it's gone in some interesting directions. What would the walls look like inside a spacecraft? It would have to be ultimately renewable biosphere. Okay? There's no way to stop and replenish your resources. So this puts you in a position where you have to have an ultimately sustainable architecture. So a world ship is usually what we call a spacecraft that's occupied by humans. And we have some advanced systems also, warp drives, metric engineering, using extra dimensions. These are all things that we have the physics to explore. They're very, very far-reaching things, and they're fun. People want to research it, so we make a team. But we have interesting things like a CubeSat mission. So can we take a very, very small spacecraft, just one square, 10 by 10 by 10 centimeters, put a whole bunch of thrusters on it, and fling it on its way to Alpha Centauri? Just to set a mark and say, catch me if you can. Nothing is on its way to Alpha Centauri right now. Humanity needs to set a vector. Project Icarus didn't sit behind while we were developing these other projects. They came back with a lot of other work. We designed numerous permutations. This is Starship Resolution, which cleans up some of Daedalus's problems. This is another fusion project called Firefly, which uses a magnetic confinement fusion engine. This is another spacecraft that uses ultra-dense deuterium, which is a theorized state of deuterium, which, if we found, would make an enormously dense power source. And we have some pirate ships here also. This is a Ghost. This was sort of a special that we announced during Halloween, that just passed us. And we saw that all this stuff was good, so we had a party a couple of months ago. We had a conference called Starship Congress in Dallas, which was awesome. We looked at how we could progress from now to near interstellar future and to deep future, like what technology would we have to pave. And we had some wonderful attendance. Michael Minovich was the gentleman that discovered the gravitational assist. So a spacecraft curves around another planet and picks up momentum and is able to explore the universe. So every space mission uses a gravitational assist. Dr. Michael Minovich we had the honor of having Dr. Minovich there. Dr. Winterberg is the inventor of the fusion engine that the Daedalus used. He's still alive and kicking in his 80s, completely clear, sharp mind, and tipping his hat to offering his assistance. But we want more. How can we get more people involved? And I figured that we figured that hardware development is the key. We want people touching things, building things, not just these paper studies. Like, what can I manipulate? So we've recently had the extreme pleasure of adding Drexel University's Icarus Interstellar chapter to our fold. This is the first interstellar research chapter ever, and Icarus's first interstellar research chapter. 50 people attended the inaugural meeting, 40 people joined. 40 students. That's very important for us. Rutgers University is doing research in interstellar engineering now for the reaction chamber for the Daedalus. Research for interstellar spacecraft has never been done. We formed a makerspace in Anchorage, which is where I live, because I wanted to take everyone and show that everyone can participate in this. And we set some goal. We want to build some thrusters and things like that. So these are two friends of mine, Jeff Blum and Henry Lee. They built a pulse jet thruster in just a couple of weeks, because these guys are hyper builders, machinists, amateurs. And they know their way around 3D printers so that we can model the spacecraft. Daedalus models and things like that have never been created, so we can explore, how these things are built and put together. But we come up with some crazy ideas every now and then. What if we needed to? Someone mentioned that algae would be a really good way of producing fuel, of producing food stuff in orbit. And someone said, "Oh, I think they can make alcohol, so let's make some vodka." It would be interesting how much that would go for. But others have similar ideas. Dr. Alan Bond was the Daedalus project leader, and he's currently chief scientist for a project called Skylon, which objective is a single stage to orbit rocket. So one rocket capable of delivering a payload into orbit, no stages, it delivers something, it lands, it refuels, it delivers something, it lands, because we need to get material up in space quickly. I'm currently working with a company called Variance Dynamical, for which I'm the chief scientist, on radiation-hard electronics, because you can't just have radiation ruining your systems there. That's kind of a waste of things. So radiation-hard electronics and sensors are very key for surviving and communicating, and it also have spin-offs to communication systems on Earth. We're not the only ones. There are people who are investing in space and far future space exploration because they understand why space is important. It's a driver for improving the quality of life on Earth. One of our future aspirations is to start an academy that's dedicated to interstellar engineering, where we take students and we give them the most difficult tasks and just watch what they come up with. I don't know if I can come up with any great ideas anymore, unfortunately. Maybe a couple left. But you look at an 18-year-old or even a 14-year-old or even a 10-year-old, how they approach problems which haven't been put into that dedicated way of thinking, and they come up with innovations. So let's fuel innovations, and let's give children a place to live and work in space so that we can have a future in space. So how would we find all of these people? How do we reach out to all of these people to try to welcome those interstellar accomplishments? And that's by starting a prize. And we call this the Black Sky Thinking Prize. Not a blue sky thinking prize, but a black sky thinking prize, where you're not on the surface of the planet and there's no limitations. Could you run the video, please?
I love this idea of black sky thinking. It reminds me of Marina Benjamin's line from Rocket Dreams when she says, "When we dream of space, we dream of transcendence. We dream of what we might become. like a caterpillar before turning itself into a butterfly. We need to create the conditions for a cultural inflection point. We need to realize that we are evolution becoming self-directed. We need to realize that what it means to be human is to transcend our boundaries. We didn't stay in the caves. We won't stay within the biological straitjacket of our current skin bag. We transcend our boundaries. We use our technological scaffoldings to turn ourselves into something far greater than what we were. Black sky thinking is a call to upgrade ourselves. It means that what it means to be human is to transform and transcend. That's what really turns me on about this notion of black sky thinking, and that's why I think it's worth celebrating.
It's my strong belief and a dedication in this mission that there's no greater achievement than reaching for the stars. By researching the stars, we'll make the solar system our playground. And if we start now, then our children will inherit the universe. This is our mission, to build a starship. Thank you very much.
Thanks, Andreas. We are running over time now, so we've only got a few minutes for questions. I'll start with a silly one. In terms of fueling your project, have you thought of harnessing the energy of Jason Silva? Because he's pretty energetic kind of guy there.
Frank De Silva, exactly. If we could strap a couple of electrodes to him, he could do a wonderful job.
So, in terms of we are looking for life, as you say, and in the huge numbers that we have out there that you were quoting, it seems like there must be some life out there somewhere. If we do discover some place that is or has been supporting life, what do we do with that information?
I ask my students the same thing, and they come up with remarkable answers every time. If we found a planet that had life, but it was inhospitable to humans, but there was teeming life, intelligent life there even, and we found another planet in the exact opposite direction that could harbor, that could host us, humankind, which one of the two would you want to explore first? And almost undoubtedly, they go for the planet where we could survive in. We're interested in searching for life on other planets, but when given an option from several years of asking students, the key sort of motivator is survival, really. Because we're at an age, we're at a state of technological evolution where humanity can actually protect itself from some certain threats. We can spread out to other planets of the solar system. There are asteroid threats that continuously, that we're exposed to asteroid threats continuously. We've known that it's happened at least once before, probably a couple of times. There could be a mass extinction on the surface of the planet. And like what happened in Russia just last year, that asteroid that hit Russia was 100 times more powerful than the Hiroshima bomb. And remarkably, no one got hurt. No one got hurt. That was a shot off of our bow. And I have a, what keeps me working is a sense of duty, but a sense of embarrassment also, because imagine what would happen if there was an asteroid that was discovered, and we've got 1 year. It's a massive asteroid, and we've got 1 year. It's going to hit the Earth, and there's nowhere to go. There's nowhere to go. It's going to hit the Earth. It's coming from the direction of the sun where we can't detect them, and it's going to hit the Earth. How embarrassed would I feel? How embarrassed should we all feel that we had this capability in the 60s to continue exploring the moon. The Saturn V was capable of delivering people to orbit, to Mars orbit. It was produced to be a catch-all to continue. And there was going to be a Saturn VI and a Saturn VII and a Saturn VIII, which was going to take people to Mars. We could proliferate the human race, if only to survive. But we choose not to, for political reasons. How embarrassed would you feel if you couldn't back up your own civilization when you had the capability to do so?
At the same time, Andreas, we live in this prosaic world of the global financial crisis, and we have a US budget deficit that is threatening all of us. And I certainly know in this country we're obsessed with having a budget surplus. So, are we still pioneers? Are we still dreaming big, with that sort of small $18 billion NASA budget?
I think that we all saw NASA as our champions. When we meet a NASA scientist or a NASA, there's a certain sense of awe. Oh my gosh, he's a NASA scientist. Must be brilliant, incredible intellect, and incredible creative capability and technical capability. But that's not true anymore. Even amongst the people that I know, they've been some bad sayings have been drilled into them, and the worst one is that I heard from several NASA engineers is that better is the enemy of good enough. Better is the enemy of good enough. This destroys progress. This destroys progress. So when your champions are in need of assistance, that's when the people step in and help them along, slay that dragon. You don't just put the knight in front to go and conquer everything. You get the townsfolk together with pitchforks. And that's what Icarus Interstellar is trying to do. Get all of those people who have the capabilities, who have math degrees, who are plumbers, who are machinists. You saw what the Anchorage Makerspace was doing. All of that stuff happened within the last 3 months. They built the thruster. Gave them a couple of schematics and they built it. Because there's unbound creativity locked up in the human spirit. And we just need to unlock it. And one of the sort of problems with nationalized space exploration is that it's recluse in a sense. Like if I'm not a NASA citizen, if I'm not a U.S. citizen, or if I apply for NASA and I don't get hired, I can't work on this mission because it's theirs, right? So what do the millions of people that have access to the internet and that have access to this massive library and this creativity, what do? They're excluded from this effort. They're excluded from space. The important thing is to feel like you can participate, vote, do something, affect change. So if you can take space exploration and bring it to a very base level where everyone can participate, even if it's at the volunteering level, then your potential for creation and your potential for transformative change goes up dramatically. And you also have people who care. If you're a part of it, then you care. Space has been ignored. We went to Mars. We're sending a mission to Pluto. People are more interested, I was joking with some of colleagues yesterday, people are more interested with when the next iPhone update is coming out. A spacecraft is about to approach Pluto. We're going to see Pluto for the first time. But iOS 7 is also being released on the same day. Maybe I'll minimize that screen. It's going to launch, whatever. So how do we change that?
Ultimately, whose responsibility is it? Because, we're now seeing, for instance, India getting involved in a space race with China, and India, as we're going to hear in just a moment, has got its own very sort of fundamental developmental problems. They say that it's not enough money to do things that we need to do down here.
Yeah.
How come, who's going to find the responsibility to make money available for what's happening up there?
Where do you find the money to do it is a great question. How do you find the money to protect children, to build houses? How do you find the money to do things that are meaningful for humans? And I think that's something that every professional probably in the room has experienced. I have an aspiration, I have a goal, and then I'm going to keep on grinding on until I can find the money to do it. I can't answer globally, where will the world find the money? My approach is I'm going to try to do as much as I can with the resources that I do have. So Icarus Interstellar has produced, we calculated it once. If we put everyone that volunteers for Icarus Interstellar, we have approximately 200 researchers right now. Last year we had 76. 3 weeks ago we had 150. Right now we have around 200 researchers. We're going to probably have about 1,000 members within about a year and a half. And it's not going to stop. It's not going to stop. Because people want to explore space, and they're willing to contribute the most incredible research, which is their time and their skills and their capability and their creativity. We calculated around $4.5 million worth of research contributed to Icarus Interstellar by NASA engineers, by professors, by amateurs. That's a resource to capitalize on.
I've been told we have to move on, but I'm going to squeeze in one last question, Andreas. Does your space research inform your sort of philosophical worldview about the big questions about who we are, how we originated, and so on?
It does. It does. Some people look to our history. I've always looked to our future. It's a very, very personal thing, but I don't feel like I don't feel any sense of importance of who I am and what I'm doing right now, and I try to measure everything with what my children are going to inherit. So if I can inform sort of the human condition, if I can imply a vector, a trajectory for the human experience, for what humanity can live through, can experience, do we have fusion energy, ultra clean, compactified energy that doesn't harm the environment, then that will come from fusion technology, and that is something that we develop as part of developing Starships. If there's a growing problem with water and irrigation, so you can't have a spacecraft that's traveling to another star running out of water because there's no wells. So how do you recycle that water? That technology from the spacecraft will find its way into society. How do you, what happened to the biosphere projects? There was Biosphere 1 and 2. They had plants in this jungle and people went in there, kind of a hippie kind of thing, right? They went in there, they were going to live in this biosphere for as long as they can. And they didn't do very well at all. Really, they found that the waters turned toxic pretty quickly. There's, too many ants. They were complaining. If you go back and you read the reports, they were like, we don't understand what's going on. Why are these ants? Why is the ant population growing? Well, try to figure it out. Don't just cry and open the door and go outside. That's what the benefit of designing for a Starship is. You don't have the benefit. You have to put yourself in the most difficult condition. If there was even a conceivable possibility that you could open the door and bring in some ice from an asteroid or something like that, you can't do that when you're traveling at 10% the speed of light. It's going to destroy you. Okay? So you have to look for extreme solutions to extreme problems. Or what about shielding issues, for instance? There's all this radiation and things like that. People worry about nuclear power. And there's a fear there's a fear of nuclear power, but it's the highest energy density power source that humanity has. There's no two ways about it. And fossil fuels are causing all of these problems, and they're cumbersome, very cumbersome. You have to mine it, you have to transport it. Its efficiency is really low. What we need is more research into nuclear power. And nuclear propulsion is a spin-off. And that could make a whole bunch of problems go away. And if you could produce a material that could shield you from it sufficiently, then the same way that we travel in our vehicles, because we have advanced materials, we can travel in our vehicles within certain speeds that are considered safe now. That doesn't happen without continued research.
Okay, if you have more questions for Andreas, you're going to have to save them for lunchtime and sort of collar him and put him to the test. That was amazingly exciting presentation, Andreas, and it was a lot more inspiring than I was expecting it to be. So thanks very much for that, and thanks for speaking to us today, Dr. Andreas Tziolas.